Who has heard of a galaxy before? So pop it in the chat if you've heard of a galaxy before and if you know what it is. Okay, so we live on planet Earth, which is in the solar system. And the solar system is a group of objects which orbit the sun. And our sun and the solar system is just one of billions of stars in their solar systems in the Milky Way galaxy. And every time you look up at the stars in the night sky, you're seeing stars in the Milky Way galaxy. So we have our Milky Way galaxy, but our galaxy is not the only galaxy out there. There are billions of more galaxies in the universe, and every galaxy is special and different in its own way. So in this image here, I really love it because each little dot is actually a galaxy. So they're all really different and they all look, yeah, they're all really different and special in their own way. So are all these galaxies the same? No, you probably guessed from these different photos and from back here as well that they're not the same. There's different types of galaxies which we'll look at here. So the first type is called a spiral galaxy, and a spiral galaxy is a flat galaxy which has and rotating, which has different spiral arms which have gas and dust throughout them. And these spiral arms contain actually star-forming regions. So throughout the spiral arms, stars actually form in them. Elliptical galaxies, on the other hand, are a big, giant, massive stars bunched together in the shape of like an egg, basically. They look, yeah, it looks like an egg. And they're quite large. They're a lot larger. They're very old, and they contain not as much. Very little gas and dust, and so they don't really form stars as often as spiral ones do. And over time, spiral galaxies actually lose their spiral shape and they slowly evolve into elliptical galaxies. So spiral galaxies, we believe, are younger than elliptical ones because they burn through their gas and the star formation slows down. The last type of galaxy looks like neither of them, and this one is called an irregular type of galaxy. So these galaxies don't look like spiral or elliptical galaxies, and they can just be formed this way, or they can be the result of different galaxies crashing into each other. So I've got this really cool simulation here, which actually shows the evolution of gas in galaxies over time since the Big Bang. So you can see the dust and the gas will start to clump together and interact, forming new stars. And when there's enough mass, gravity will start to pull all the stars, the gas and the dust together to form a galaxy. Galaxies can even interact or collide with each other, but there's actually so much space that the stars generally move past each other. The gas clouds and the dust that do collide with each other from each galaxy can interact and form new stars. Yeah, so I really like that simulation. So there's many different regions in a galaxy, and I'm going to use the Milky Way, which is a barred spiral galaxy, as an example. In the center of the galaxy, you have a supermassive black hole. And to answer, I can't remember the name of the person's question, but we believe that most galaxies have a black hole, but we've actually identified galaxies that don't have one. So then we have the spiral arms here, where we have all different molecular clouds and and to give you an idea of how important resolution and scale is in astronomy, I'm going to make a comparison. So take these maps of Canberra on the left, for example, and the right here. the scale on this one here is actually too big to make out any details in camera. And you can only see sort of the prominent features like the lake and really big roads and sort of towns next to it and so on. But if you zoom in, you can see that the scale increases, and the image here, you can see a lot more details like roads and streets and suburbs and so on. And this idea is the same in astronomy. Without a high resolution, we wouldn't be able to make out all the small but important features in galaxies. So up here, you have the Andromeda Galaxy. And so this is the whole galaxy, just the whole field of view and the entire thing. And then below is actually really, really close up view of the galaxy. And it's really high resolution, which means we can make out all these amazing details like the star forming regions and molecular clouds and so on. So there's many different ways of investigating and studying galaxies, but one of the most important techniques in an astronomer's toolkit is actually called spectroscopy. So have you ever learned in school when you have a prism and you shine light through it and you get a rainbow of all different colors? This is what spectroscopy is. It's when the light is dispersed or scattered or divided into all these different colors. These colors correspond to different wavelengths and form what is called a spectrum of different colors. So for example, when we collect light from the sun and we detect all these different colors in the spectrum, this is the image that you'd actually get. You'll notice that there's different little black lines, vertical black lines in the spectrum. And this is because the spectra of stars like our sun, they aren't perfect smooth rainbows like here, but instead they contain these black lines called emission and absorption lines. So when we use spectroscopy to study the spectra of galaxies, we are in fact studying the combined light from billions of stars and gas and dust in the actual galaxy. And the spectrum of the galaxy can provide, or really any astronomical object in the universe, you know, a galaxy or a star or a jet coming from a galaxy, it's unique, like a fingerprint. And studying these galaxies using spectra can allow astronomers to determine all different properties about the object, such as its chemical composition, its age, the temperature, formation history, and even how far away it is. So in the top image here, we call this an emission line spectrum. So you've got the rainbow of different wavelengths or different colors, but then these big spikes here, they are called emission lines. And these emission lines occur when the galaxy or the star or the object we're looking at emits only certain colors or wavelengths of radiation. And then in the bottom image, we have a spectrum, but instead this time there are dips. These big dips are called absorption lines and occur in space when something comes between the object we are studying and our detector, or between us. For example, a cloud of dust or interstellar gas. So the cloud of dust or gas absorbs certain colors, for example, leaving the rest of the light to come to us for us to detect. So yeah, now that I've explained what emission lines are, how do we actually use them to study galaxies? So to remind you from before, spectroscopy, we use spectroscopy and detectors to split up the light from galaxies into different wavelengths. And you can see this image of the galaxy here is split up into all different wavelengths. And this is because the reason why this is so important is because different wavelengths correspond to different elements and they can provide different amounts of information. There's different amount of light detected at each wavelength or color. So certain regions in the galaxy will be brighter at certain colors than others. So when it's really, really red or orange you get it's really, really bright and you get a lot of light. And then as you go towards the more blue or purple ultraviolet wavelengths, you don't get much light at all, or you only get light sort of around the edges or the outskirts of the galaxy. And in fact, I actually use emission lines to study galaxies in my research. So I'm currently writing a paper on the galaxy NGC 3109, which is a really close irregular dwarf galaxy. It's very close to our galaxy, the Milky Way, and it's in the local group. So I use emission lines to not just study the galaxy on the whole, but to study specific regions in the galaxy called specific star-forming regions in the galaxy called H2 regions. So these star-forming H2 regions are really important because when we study them, and by studying the conditions and environment in which stars form, we can find out about how galaxies evolve. So you can see again here that similar to the image before, I mentioned resolution. The resolution of my galaxy is actually, it's pretty good. So we're able to make out all these really important details like the H2 regions. So yeah, this galaxy is actually part of a survey called Typhoon, which images about 100 of the closest nearby galaxies. And the reason why they pick the closest is because we can have a high resolution and be able to see all these details. So the image here, here is called the composite image of the galaxy, and it's at multiple wavelengths. And this image here is just at one wavelength called H alpha. And these images here, these are plots that I made for my paper, and they are actually different plots or different plots of the galaxy, different images of the galaxy, but at different wavelengths. So this is the image of the galaxy at H alpha, for instance. This is one particular wavelength, and they look different because the galaxy, the light from the galaxy is stronger at certain wavelengths or certain colors than at other wavelengths. So for instance, here you have the color bar here, and it's really, really bright up here. The more yellow or orange you get, it's very, very bright at H alpha. And then as you get darker, it gets quite weak. So the N2 emission line here, and even O3 is not as strong as H alpha. And for that reason, we use H alpha, the H alpha emission line, to study H2 regions because it's bright, we have a lot of light, and that is what allows us to identify the H2 regions. So yeah, that's basically, that's my research, basically what I'm doing now. And I'm working as part of Lisa Cooley's Star Formation and Galaxy Evolution Research Group at Australian National University at the Research School of Astronomy and Astrophysics at Stromlo. So I work on that as part of, alongside my studies, and I, very much enjoy doing that. Thank you very much, everyone, for listening.